Hello student, welcome to today's session. So since last 1 month, I am getting a lot of queries in regard to the topic of benzyne, questions in and around the benzyne. So I thought of placing one video on this. Hopefully by listening to this, discussing this particular topic with me, you are able to understand the apprehensions and doubts which you get across this particular topic of benzyne. So we will be addressing this topic through the problem solving, as is the endeavor of this particular series is to uh, address theory through the problem solving. So let us pick up first problem and then we'll address this problem is being sent by someone, and it's a beautiful question to begin with. Orthobenzene diazonium carboxylate salt, this is being said like this, on heating gives A, which may undergo dimerization to give B. So you have to identify what are A and B. So first in this question, we have to address the thing that what exactly is benzene diazonium carboxylate, orthobenzene diazonium carboxylate. So this we know that if I would write it like this is what you call it as diazonium salt, isn't it? And when you talk of carboxylate, this is what you are saying it has to be carboxylate, and these are ortho to each other. And if I would write its IUPAC name, it would be benzene diazonium 2 carboxylate, because at the second position you would be having the carboxylate. Now the fellow is saying that this is being heated. When you are going to heat this out, what basically you are going to get here in this case is this bond comes here and this goes here. Wow, this is very interesting, and you would get with a compound which we are referring to it as benzyne. This particular species we are addressing this as benzyne because there is a generation of a triple bond here which make it as ine. Instead of in the benzene we used to write it like ZEN, E. Instead of this E we happen to get YEN. So that is what you call it as benzyne. Now, further he said this benzyne may undergo dimerization because this is a reaction intermediate and can be can be isolated as well, but it is very easily undergoes dimerization of this type. This triple bond opens up like this, and this results in a formation of a compound which we are referring to it as biphenylene. So this is very interesting, and I am leaving you with one question, that would you be considering this particular entity? This is the common name of this compound is biphenylene. This is the common name of this, and this we said as benzyne. So there are two questions here to address with. Are these two things aromatic or not? This is a very interesting one. Are these aromatic or not? Now, aromatic species or not, this is what we are going to see in the further discussion as well. Because if I consider this part only, it seems like anti-aromatic, and if I consider this part, it seems like aromatic. So now you have to see into it whether it is aromatic or not. That is also we are going to address it here. And as a matter of fact, this particular species, which we said benzene diazonium carboxylate, actually is being formed from intranilic acid. Now, what orthointranilic acid is this compound? Orthointranilic acid. This is what you call it as orthointranilic acid. Intranilic acid. Orthointranilic acid, if happens to undergo diazotization reaction, this leave us with a compound which we are referring to it as benzene diazonium carboxylate. You might all be knowing it, that you are going to get this particular species, because here you should know that whenever you have any primary amine with you, any primary amine, when treated with HNO2 in presence of HCl, or other way around sodium nitrate in presence of HCl, you always would end up getting diazonium salt. Now how you can remember this is one trick I can play here, that you just would remove out, this is a shortcut, not an exact viewpoint about it, we can do its mechanism as well. that whatever is the number of, just see here, how many hydrogens do I have? Two hydrogens here, one hydrogen here, one hydrogen here. So in total, I have four hydrogens, and there are two oxygen atoms. So two water goes out, and you are left with one nitrogen this, another nitrogen this. So you end up getting this particular species along with its counter ion chloride. So this is benzene diazonium chloride. And this particular reagent, the combination of these reagents, any of these two combination can be said as diazotizating reagent. Diazotizating reagent. This is very important from the standpoint of view of JEE mains, advanced or NEET examination. Now, how this is being generated? Sodium nitrite treated with HCl. This is a simple salt, and this undergoes a reaction to form nitrous acid. This nitrous acid, shelf life of this acid is very less, so it is being generally generated in C2. In C2 means within the reaction mixture it is being generated from these stable compounds. So you have taken primary aromatic amine. What is the condition to generate a diazonium salt? You should be having primary aromatic amine treated with nitrous acid in the presence of HCl to give you nitrous acid, which in a way would then produce that benzene diazonium salt. Or this I can also write it like this also. Now if you would push me to write its mechanism, it is not very difficult, it is very easy. So you have taken, if I would write it here, you have generated in C2 nitrous acid, and this nitrous acid is then being attacked by the H positive from HCl. This is from HCl. This would attack this lone pair and resulting in the formation of protonated nitrous acid, and this protonated nitrous acid loses out water to this water goes out, and you would get a nitrosonium cation. Nitrosonium nitrosonium cation. This particular cation then would attack the aniline. This is what we are writing it as aniline. Aniline's lone pair is being attacked by this electrophile like this, and this would generate something like this. Now it is not a very difficult one, it is a easy one. The positive charge which the nitrogen is having of nitrosonium cation got removed because the lone pair of the nitrogen of aniline comes here for the bond formation. So as a result, this would get a positive charge. Now what you can do is just do the deprotonation from here. This H positive attaches to this lone pair and leaving out the positive charge on nitrogen as such. Um, the nitrogen's positive charge get removed, and you end up getting something like this. Here you would generate a positive charge. In one step you can also show it like this, or if you would like to go in a proper way, so that would take a bit of time, and you would get this as a positive charge. The positive charge which was onto the nitrogen of aniline got removed, and now what you can do is this lone pair again comes here, this goes here, and this is nothing but a resonating structure. So again you would get a positive charge onto the nitrogen. Here you come the double bond, and the oxygen's positive charge got removed. And again what you are going to do is again do the protonation. This goes here, intramolecular proton exchange. This we usually speak it as intramolecular proton exchange. We did the intermolecular proton exchange, resulting in the formation of the positive charge on nitrogen got removed, and you would get a positive charge on oxygen. And lastly, what you are going to do is this lone pair goes here, and this water got out. So basically you end up getting N triple bond N and the positive charge, and the counter ion to this would be the species which we are saying it as Cl negative. Because if the starting material, these are the two starting material which in totality is having one positive charge, so the final product also would have one positive charge. To balance this out, there would be a counter ion of the Cl negative ion. So this is the way we usually get the diazonium salt. So I did the mechanism of diazotization reaction. So because this particular reaction is very important from the standpoint of view of your JEE mains, advanced and NEET examination, so you always keep this in mind. So this diazonium salt we have generated from here, Where we were. Okay, so this is the intraneolic acid. This part got changed into diazonium salt, and this result in a formation of the compound which he was referring to as benzene diazonium carboxylate, which on heating removed out nitrogen gas and carbon dioxide gas. So the driving force for this reaction, which I have missed while discussing this particular discussion, that the loss of nitrogen and carbon dioxide gas is the driving force, because this is an entropy driven sort of a reaction where two gases are going out as a living group. So this is the first question which we wanted to address with, and the answer to this question would be A would be the benzyne and B would be the biphenyl. And this is, both of these are aromatic in nature, by the way. In the next question we are going to address that one also. Now the second question, which again was sent some weeks back by somebody, that which of the following, just see into this problem. It's an interesting question. Which among the following statement may be said as incorrect about benzyne? So the first question, the benzyne is aromatic in nature. All pi bonds in benzyne are not involved in aromaticity. Two sp hybrid orbitals, and so the all these options are relating to the feature of chemical bonding. So what chemical bonding aspect is involved in the case of the benzyne? So to understand that part, we have to first see what exactly is the structure of benzene. So if I just would write the structure of benzene, benzene would look like somewhat like this. Here you have all these p orbitals. All the carbons in benzene, if I talk of benzene, are sp2. So here you have, this is a normal benzene. This is what you call it as normal benzene. In this normal benzene, there is a pi bond here, there is a pi bond here, there is a pi bond here, but it can undergo delocalization. So this pi bond can be sideways overlapping because of any of these. So as a consequence of that, we usually write benzene to have a pi bond like this or pi bonds like this, or at the alternate position. So these two are the resonating structure. Actual structure of the benzene would have a, when you talk of a circle putting here, the circle actually is not the symbol of benzene. Many times students take it like as a symbol of benzene. It is depicting this thing that we don't know where the pi bond is. That this circle is showing partial double bond character in the entire of this particular molecule. Now let me have to discuss about the benzyne. How we are going to generate the benzyne. As I said, that all these carbons are sp2 hybridized. All of these are sp2 hybridized. So there is a very interesting feature about benzyne, which I'm going to discuss now. So what basically is benzyne? You have to take out two hydrogen atoms around it. Now, if you would just see that what type of a sigma bond, this orange colored carbon hydrogen bond, do we have? So this, if I would write it here, it again is a sp2 hybrid orbital, and this also is a sp2 hybrid orbital. So there is a bond between hydrogen and carbon. If I have to mark this bond, this carbon is sp2 and this is s. So this is a sigma bond of this type. The carbon in benzene, the carbon hydrogen bond which we are referring to as sigma bond is of the type of ssp2. Now you have to remove a hydrogens out of it. Now I just to make the savage of time, I am drawing it here only. So if I would show you here that what exactly we are going to do here. Now, if I would remove this hydrogen and this hydrogen, there are two electrons in the sigma bond, and I just have removed one hydrogen out of it. So now what I am left with is, there is one electron here and one electron here. These are the two electrons, because two hydrogen atoms you have taken out. This hydrogen atom is gone out, this hydrogen atom is also gone out. So in a way, benzyne is also referred to as 1,2-dihydrobenzene. De stands for the removal. What you have removed, two hydrogens. So this also is commonly said as 1,2-dihydrobenzene. So I have taken out two hydrogens out of it, and as a consequence, now once I have taken out two hydrogens out of it, I am thinking, or you are also thinking, that if we remove these two hydrogen atoms, there would be one unpaired electron left in sp2 hybrid orbital, and which in a way undergoes sideways overlap like this. This undergoes sideways overlap. Unlike what we are expecting it to have, we are expecting the fact that here you have a triple bond. Conventionally, we will be saying that this would be sp hybridized, this would be sp hybridized. If it had been a sp hybridized orbitals, if it happens to undergo sp hybridization, it has to acquire a triple bond, and it once the triple bond is being generated, the two pi bonds which is present on a sp hybrid orbitals, they have to be perpendicular. Here also it is perpendicular. If you could see that this blue line is perpendicular to the yellow line, which I have showing it like this. These are perpendicular to each other. Now, why I'm saying that, although it seems like it is sp2 hybridized, but actually it is not. So this is the special feature in the benzyne. In the benzyne, the pi bond actually happens between hybrid orbital, that too of the type sp2 sp2. This is very important statement which you always have to remember. So this carbon is not sp2 hybridized. So here I would be writing categorically all carbon atoms in benzyne is sp2 hybridized. This always you have to remember. There is no sp-sp hybrid orbital or which is making a pi bond. Now why is it so? Now I am going to show it in a different version. That if in case, just stay with me to have a glimpse what I'm trying to figure it out here. So these are the p orbitals which are perpendicular to each other and are making a pi bond, and here you have all these hydrogens. Just see it with me, all these hydrogens. Now I am using the two carbons from here. So if in case I just would make this carbon to be sp hybridized, so then these two would be the perpendicular orbitals. These two would be the perpendicular orbitals. And already we are making a pi bond here. There is a pi bond here. There is a pi bond here. And there is a pi bond here. And these can undergo sideways overlap. Now, once I just would write it like this, that this would undergo sideways overlap, there is lot of electron density inside the benzene. If it had been a pure p orbital, if this pure p orbital is making a pi bond, then the two lobes of the p orbital would be equidistant or of same size and length and breadth in both the direction. This would go into this as well as it will come out of it, and this also would go into it and would come out of it. Now the orbitals which are going into the benzene would create a lot of repulsion, because there is already good amount of electron density above and below the plane of benzene ring. So that is why. And secondly, this carbon would always love to make a thing linear. This cannot become linear. This cannot become linear because of the rigidity. Cannot become linear. Why it cannot become linear? Because it would not have that rigidity or flexibility around it, because here it has been stuck with this carbon, here it is being stuck with this carbon in the planarity, so it cannot become linear. So what I'm trying to make it here is that in the case of benzyne, it is a unexpected exceptional case where you have the p orbitals just like this. These p orbitals are perfectly doing resonance and they are aromatic. They are sideways overlapping and they are undergoing conjugation as well. But the orbital which I am now referring to with the blue marker, this particular orbital is sp2. The inside lobe is smaller in size, as we see in a sp2 hybrid orbital. And this is the sideways overlap being done. And this particular pi bond, this pi bond is not involved in aromaticity. or you can say it's not involved in resonance. This is not involved in resonance. Other orbitals, other p orbitals, just like this one, they can undergo sideways overlap and then can undergo in conjugation as well, which is being shown by white marker. So here is a very, very important statement that in benzene, this is sp2, sp2. Generally, we people know that the pi bond is generally being made by pure p or d orbitals, or p with p or d with d or p with d. So something pure p or d orbitals is required. But this is the case where unexpectedly, because of the rigidity, because of the steric problem around the carbon-carbon bond, which is engaging a triple bond, it cannot acquire sp hybridization, nor do it acquire a sideways overlap of p orbital from the pure p orbitals. So it is sp2 sp2 overlap. So this is very, very important. Now let us see into the options. This question was really very interesting. So is benzene aromatic? Yes, we will be saying it is aromatic because it is going to adopt the condition of 4 pi 4n plus 2 pi electron. That is what you call it as Huckel rules. That is also being adopted here because there are n is, if I put n equal to 1, it is 6 pi, so it is planar. So what is the condition of aromaticity? There are four conditions. It should be cyclic, it should be planar, it should have delocalized pi electron density on the entire molecule, and must obey Huckel's rule, that is 4n plus 2 pi electrons, where the n can be 1, 0, 1, 2, 3, and so on. So if I place n equal to 1, it happens to give me 6 pi electrons. In totality, this is again a very interesting thing to refer here. In totality, if somebody would ask you that how many pi electrons are there, you can say 8, but the 6 pi electrons are engaged in the aromaticity. And I just would pass one more example in this context where the lone pair or the electron density is not involved in the resonance or in the aromaticity. I just would take one more example. All the pi bonds, let's first finish the question. All pi bonds in benzyne are not involved in aromaticity. All pi bonds in benzene are not involved in aromaticity. You should be very cautious, critical about reading the statement. Not involved. This, in a way, is a right statement, isn't it? This particular pi bond, which I have already referred, is not involved in the resonance. It is not involved in the resonance. So here I should mark it. This is wrong interpretation. This diagram is a wrong interpretation, which seems like this way, but actually it is not that way. Okay, what is the next? Two sp hybrid orbitals are used for. This is a wrong statement. sp2 hybrid orbitals are involved here in this particular structure of benzyne. Six pure p orbitals are used for pi bonding. That is perfectly right. These are the 6 p orbitals which are being perfectly used here. This is, all of these are sp2 and it is having 1 1. So here I just would mark these are the hydrogens which are also there. So this is what we come on to the conclusion. So it's a beautiful question. So here this also is a right statement, and what we are looking for, we are looking for a incorrect statement. So if we are looking for incorrect statement, this would be our right answer for a wrong option. That is what is being asked in the question. And one more thing which I was thinking of placing it is, just like if you take the case of pyridine, in the pyridine also, if you just would mark it like this, in the case of pyridine, the lone pair is in the different orbital, which is not involved in the resonance. Although this species is aromatic, this is what you call it as pyridine C5H5N. This is aromatic species. All the carbons are sp2 hybridized, and this can undergo resonance like this, or this may also undergo resonance like this. So perfectly delocalized, but this lone pair is not involved in aromaticity. So this also somewhat like that. Uh, Same thing, same sort of thing is happening in the case of enzyme. One of the pi bond is not involved in the resonance. Thanks a lot. I hope you have enjoyed this particular session, and if in case you find it well, do write wow, and it would really motivate me to place more videos of this this type where there are a lot of apprehension in the question. Thanks a lot. Have a nice day. Stay safe and take good care of yourself. Bye bye. Take care.